Hello, my dear. I welcome back. Okay, so today we'll start. This is the third. I think this is our third session. In this one, we will discuss about that first law. That means the first law for a revision part of that smart revision. So in this one, we have to discuss about the open system with on a steady state, and also we have to think about that what is the closed device. That means in the steady state also and on a steady state also. So what is that in this case? In this slide, what we have in this one, see, already we have to done with the flow work. Okay, so there is a recapitulation of that one. What is the flow work? Flow work, it is nothing. The fluid want to flow, so to maintain the fluid flow, there is a work. We have to apply the work for the we have to that means the fluid, that means if this is a flow of the fluid, due to the pressure difference, the fluid is flowing due to the pressure difference. As we know that the fluid will flow have a different mechanism, different mechanism. So if the fluid is flow with the help of the pressure, in that case this flow work will present. So this work is the property of the system. This work is the properties of the system. So my dear, in this one, this work is the property of the system, and that means say this one, the work or energy required to push the mass into or out the control volume, this work is necessary for maintaining a continuous flow through the control volume through a pressure difference. That means flow work, flow work, it is always per unit mass is equal to pressure into a specific volume or pressure by density. Pressure by density, that means P by rho. P by rho. So this is your flow work. This is your flow work, also called pressure energy. Pressure energy. This is also called pressure energy. Okay, now, so this is your control volume. That means, and it is a pushing kind of the force. It is a pushing kind of the force. Now, my dear, and we have already previously we have to discuss about this slide also. What is the main important thing in this slide? The main important thing in this slide is that, okay, sir, what is the important thing? If the fluid is flowing, if the fluid is flowing, the energy, that means if the fluid is flowing, so the energy per unit mass, that means this is represented by theta, energy per unit mass that have a enthalpy plus kinetic energy per unit mass plus potential energy G into Z. So in this one, the enthalpy term come into picture, and in this case, the internal energy come into picture. So in this case, the internal energy come into picture for the non-flowing fluid, and for flowing fluid, enthalpy come into picture. All these things are same, remain same. Now, so if we derive the equation of the control volume system, what is mean by that? This is nothing. This is a minus sign here. So this is your minus. Okay. So what is that? Heat transfer and work transfer. So heat minus work. Heat minus work. What is the conservation of energy? Says the energy transfer is equal to energy change of the system. So this is for the system only. So system, that means this energy, this is energy transfer, and this is the energy of energy for the system at what? At each exit. That means this is at a cross section, my dear. This is at a cross section. That means each exit, that means at exit condition, and there is an inlet condition. So what is that? Exit or inlet. So this equation applicable at the section. At the section. What is that? What is the mass is exit multiplied with that total energy. So this exit, this is your exit, yeah, inlet due to the mass. So mass, if the mass is there, and there is a flow, so associated with the mass, what is the energy? enthalpy kinetic energy plus potential energy at exit minus mass inlet is enthalpy plus, that means exit minus inlet is your energy associated with the mass transfer. This is the energy associated with the mass transfer, and this is the energy which is associated with the heat and work. So heat and heat difference of heat and work is equal to mass exit with corresponding to the energy minus mass inlet corresponding to that energy. So corresponding to that energy for the open system is what? Open air non-flowing fluid is what? Enthalpy kinetic energy plus potential energy. So this is your enthalpy kinetic energy plus potential energy. Now my dear, if you rearrange this formula, this is your required expression, which is very easy to understand. What is that? This is your required expression. This is your required expression. So this expression is what? This expression is the steady flow energy equation. So this is your steady flow energy equation. That means steady flow energy equation. That means the energy transfer is equal to mass, and we have to take mass here common. Why? Because in generally there is a mass that will be single inlet and single exit. In the engineering, many questions are in the gate. There is a single, otherwise if there is a 2 exit, so there is a 2 value, there is a 2, that means M2 plus M1, and if there is a 1 inlet, so if there is a exit, let's suppose M2 and M3. So corresponding to M2 you have to write down this one into multiply with that, plus corresponding to M3 you have to multiply with that, minus inlet, let's suppose M1. So 1 inlet, and let's suppose there is a 3 exit. So M1, M2, M3 like. So we have to multiply corresponding to that energy also. Okay. So this is your precisely equation. Now my dear, this equation is what? Mass flow rate. This is your mass flow rate. This is your mass flow rate. Mass flow rate. What is the mistake to apply? In generally the student, what they have to mistake here? The mistake point is that, sir, see, this enthalpy, what is the unit of this enthalpy? Generally in the question it is given in the form of, what is given in the form of? In the form of kilojoule per kg Kelvin. It is in the form, in this form, kilojoule per kg Kelvin. Now, so not kilojoule, this is an enthalpy, that means this is an enthalpy is what? H is equal to C delta T. Okay, no problem. Kilojoule per kg. It is in which unit? It is in kilojoule per kg. Okay. So, and what is this unit? What is this unit? Please tell me. What is the unit of this one? Meter per second ka whole square. What is that? Meter per second ka whole square. So not kilojoule. This is kilojoule beta. Kilojoule. Okay. So this is kilojoule per kg, and this is meter square per second. If you convert this one, this is joule per kg. Joule per kg. Now this is your kilojoule per kg. This is your kilojoule per kg, and this is also kilojoule per kg. So intuitionally you have to multiply with the 1000. That means if you convert kilojoule by, you have to multiply with 1000 value. So 2 into 1000, always remember here, multiply with the 1000. When if there is a enthalpy, it is given in kilojoule, always multiply from this kinetic energy term, from this in the kinetic term, always divide 1000. Don't mistake. I will solve this problem also. So this is a precisely equation. So what is our main equation? The main equation is heat transfer minus work transfer. Very easy, very easy. Heat transfer minus work transfer is equal to mass transfer into enthalpy change H2 minus H1 plus change in kinetic energy V2 square minus V1 square by 2 plus change in potential energy G Z2 minus Z1. This is your precisely the energy equation. Now in this one, this equation is generally in kilojoule per kg. So in this one you have to multiply 1 by 1000, then it is in kilojoule, all other are same. So these are the simple equation. Now if you apply this equation in this situation, let's suppose there is some very basics problem is there. What is there that in this question? Please see this, read this one, and what they says that there is a heating section. So this question is related to beta, my dear, heating of a, one second, this is related to heating section. That means there is a heating section is there, na? One second, yes. So this question is related to, it is like that. Electrical heating of air in house. This is your electrical heating of air. Electrical heating air. That means this is your electric heating. Electric heating of air in a house. Clear? Clear, beta? Now, my dear, what is that? See, there is a, let's suppose there is a, this question I will read. I will read this question. What is the question says that the electrical heating system used in many houses consists of a simple duct with resistance heaters. So this is a resistance heater. Air is heated as it flows over resistance wire. Consider a 15 kilowatt electrical heating system. Air enters the heating section at 100 kilopascal and 17 degrees centigrade with a volume flow rate of 150 meter cube per minute. If heat lost from the air in the duct to the surrounding at a rate of 200 watt, determine the exit temperature. Determine the exit temperature. So what is that here? Please see this one. What I will do here? See. So this is a steady device. So MCV is equal to 0. Energy of control volume is equal to 0. And also it is stationary. So change in kinetic energy and change in potential energy, it is 0. You have to take like that, okay? Now, what is the energy analysis? That means Q dot minus W dot is equal to M dot. You have to write simply H2 minus H1 plus V2 square minus V1 square by 2 plus Z2 minus Z1. Clear? Now, my dear, here there is no any change in kinetic energy, no change in potential energy. There is a heat. So here what is the heat? Heat is your out. This is your out. So heat out, it is a negative. Heat out, it is a negative. So this is a minus Q dot out minus work in. There is a electrical work in W electrical in, and work in, it is a negative. So minus of W electrical in is equal to M dot H2 minus H1. That's it. That's it. Now, my dear, what is the value of M dot? What is the change in enthalpy for the air? Why? Because air acts as ideal gas. Ideal gas. So ideal gas, what is the enthalpy change? Delta H is equal to Cp delta T. So M dot Cp T2 minus T1. Okay. Now here, what is that? W electrical dot in minus Q out is equal to this much. Now my dear, the main thing is that here, how to find this mass flow rate. How to find this mass flow rate? Please reply in the comment box. How to find this mass flow rate? Why? Because there is a volume flow rate, it is given. So from the volume flow rate, how to find the mass flow rate? From the volume flow rate, how to find the mass flow rate? Please tell me. Density, it is not given. Density, it is not given for the air. So simply we have to apply C. See my dear, density is equal to, how to find? To find density, okay. To find density, please note down. To find mass flow rate. How to find mass flow rate? How to find mass flow rate? Density is equal to mass flow rate divided by volume flow rate, simply. But the density is not given. Density, it is not given. Then the second step is that, sir, 1 by a specific volume is equal to density, mass flow rate by volume flow rate. Now, but in this question, a specific volume it is not given. How to find a specific volume? So this is your first step in your mind. This is your second step in your mind. And what is the third step in your mind? Sir, air. That means air is there. What is that? Air. What is that, beta? Air. Okay, na? Air is there. So for air, okay, what is that? P into a specific volume is equal to R into T. Yes or not? So if you take volume flow rate is same. So if you take V is equal to R T1 by P1, just apply this one. So put R value. What is the R value of air? You know this thing, R value of air, 0.287. R of air is 0.287 kilojoule per kg. So put R value of air, put T1. What is the T1 value here? T1 it is given. The temperature it is given. How much? 70 degree. Always put here in Kelvin. So if you write specific volume is equal to R 0.287, T1 17 plus 273 divided by pressure. How much the pressure? Pressure always kept in kilopascal. So that is your 100. So this is your 100. So my dear, if you apply this equation, please note something. Pressure it is always in kilopascal and temperature it is always in Kelvin. These two things always keep in mind. Otherwise the problem is very, very high chance to get mistake here. So what is the specific volume? Please find it. What is the specific volume, beta? If you put that value, the specific volume is 0.832 meter cube per kg. Meter cube per kg. So you have a specific volume. You have a specific volume. Multiply with the volume of flow rate. So mass flow rate is equal to, mass flow rate is what? Volume flow rate divided by the specific volume. What is the volume flow rate it is given? Volume flow rate is 150 meter cube per minute. Convert it in second. So 150 divided by 60. Why? Because it is in minute it is given. And a specific volume it is your 0.832. Please resolve this one. So this is 3 kg per second. So you have this value mass flow rate put here. That is the one thing is there so to do the activity. So put all this value here. If you put all this value, what is the electrical work here? What is the electrical work here, beta? The electrical work, it is your 15 kilowatt. So this is your 15 kilowatt minus Q watt, it is your 200 watt. Please mind it. So it is your 0.2. Mass flow rate, it is given 3. Cp of the air, we know that 1.005. T2 we don't have. T1 we have. Put 70. Don't bother about you have to convert it in Kelvin. No. So what is the value of T2 here? If you find the T2 it is your 21.9 degrees centigrade. That's it. That's it. So exit temperature will be increase very minimum. Why? Because there is a heat loss. So this is your T2 value. Understood? Understood this concept? Clear? Clear everyone please? So if you clear, then we have to go to the next content part, and really this is the very important thing I'm telling you. This is the process which is very encountered in the engineering problem, engineering practice, that is known as throttling process. So my motive of this classes is that, one second, excuse me. My motive of this classes is that, that means I left one question in your mind so that you just think, and then we have to understand our concept. Okay, so what I have to see, there is a one catch is there. What is that? A throttling of an ideal gas. Please think that a throttling of an ideal gas, please read this question. A throttling of an ideal gas is approximately isothermal process. Please everyone. A throttling of an ideal gas is approximately an isothermal process. True or false? True or false? Just think. Just think. Okay. Now we have to start with that. What is the throttling process? See, there is a certain things during the throttling process. What is that? First of all, very rapid process. Very important. What is that? There is a decreasing valve. So the fluid is entry into the section, pipe section. Fluid will enter into the pipe section. That is the control volume. This dotted line is a control volume. This one is the at inlet to the control volume. This second is your outlet of the control volume. During that, you have to throttle of the fluid, throttling of the fluid. What is that? You are continuously decreasing the area between the gaps. So see, this fluid is in. One second. One second. See, this fluid is in here. This fluid is in here, and it will exit here like that. This fluid is in here, and it will exit like that. Like that. This is your throttling. So it will be, and if you are, what you have to done? You have to restrict the passes. That means you have to close the valve so that the valve will restrict. That means you have to constrain. You have to constrain that the flow will flow through a minimum area. Okay. So there is, if you are closing the valve, this area of the area of that passing through a cross throttling is very minimum. That means you have to restrict the area. What is the situation where you have to restrict the area in the throttling? What is the result for that one? If you restrict the area, very simple mechanism, ki sir, the velocity will increase. Velocity will increase. From which principle? Conservation of mass. That means a continuity equation. Same idea. In throughout the engineering, there have a 3 equations: conservation of mass, conservation of momentum, and conservation of energy. Conservation of mass generally gives the continuity equation, conservation of momentum, that means a force equation, and conservation of energy, that is your first law, that is your conservation of energy. So my dear, if you meant if the flow, that means the conservation of mass is valid, so if you decrease the area will decrease, the volume will increase. That means area A1 V1 equal to A2 V2. Now my dear, so here see this one, from here the fluid is very rapid, the motion of the fluid is very rapid motion. So what is the first term? Very rapid process. First one, very rapid process. This is the first thing. Very rapid process, this is the first thing. Now, so if there is a very rapid process, what's the outcome? Please tell me. What is the outcome? If the flow is very rapid, what is the outcome? If the flow is very rapid, please tell me, if the flow is very rapid, what is your outcome? Please tell me, everyone. I know you know, but you don't want to reply in the comment. I know that. All of you know. If the process is rapid, what is mean? Did have a two effect. What is that? First one is that very short time it will move at this cross section. That means if the very rapid, so very short time. Very short time it will cross. Very short time it will cross. Now the second thing, if very rapid, that means area minimum. That means area is, what is that? Area is minimum. That means a very rapid process, that means area minimum. Area minimum. Now, very rapid process, that means it will take a very short time to cross this cross section of the gap of the throttle valve. Now, if the area is very minimum, so the area is very minimum, that means the available area, that means what is the available area? Available area for the flow is minimum. Now, what is the meaning? What is the effect of these two? Please tell me. What is the effect of these two? Please tell me. If these two are at a time, at this, so what is the effect? Please tell me. What is the effect then? Please tell me. What is the effect? That means the effect is that means there is a very short time and also there is a very minimum. So there is no chance of heat transfer during throttling. That means so flow through them may be assumed to be adiabatic. That means very short time. Time is such a very short, very rapid, so that, and also consequently the area is minimum, so the heat transfer will be approximately negligible. So for that effect, flow through them may be assumed to be adiabatic. May be assumed to be adiabatic. So throttling is an adiabatic process. That is the first thing. I am telling you, many of the students are not able to give the reply properly. कि sir, why we have to assume the throttling, during the throttling there is a no heat transfer. That is the reason. See, it is not a matter to solve the problem. That is the matter to very crystal understanding, yes or not. So there is assumed to be a very adiabatic. That means the first outcome is throttling. It is an adiabatic device. Number second, there is no any working device. That means you are not starting the device. You are not passing the electricity. There is no. So also there is no any work transfer. Also there is no any work transfer. Now my dear, if you apply the first law, what is the first law? It says that Q dot minus W dot is equal to delta U if you assume there is a stationary. So this Q dot and W dot, it is 0. So change in internal energy, that means U2 is equal to U1. That means internal energy doesn't change during the throttling process. Internal energy doesn't change during the throttling process. Also there is a mass transfer, beta. That is true? Please tell me. That is true? Please tell me, everyone. Please tell me. That is true or not? Please tell me. That is true? So initially internal energy is equal to final internal energy. That is true if you apply the first law. Okay? But there is an enthalpy. This is so, my dear, if you think this one, that is a wrong. You don't think. Many students think like that. This is a wrong approach. Wrong approach. Why? Because while you are applying this equation, there is no any mass transfer. In this equation, this equation are not considered any mass transfer. Here is the mass transfer. So don't use this equation. So other equation is steady flow energy equation. Other equation is steady flow energy equation. What is that? Just apply this equation. Just apply this equation. Please, everyone. Just apply this equation. What is that? Heat transfer minus work transfer is equal to m dot change in enthalpy H2 minus H1 plus change in kinetic energy V2 square minus V1 square by 2 plus G Z2 minus Z1. Yes or not? Please tell me. Yes or not? Now, my dear, here we have conclusively said that, sir, there is no any heat transfer. Yes or not? There is no any heat transfer. There is no any heat transfer. There is no any work transfer. There is these two are 0. Why these two are 0? Please tell me. Why these two are 0? Why? Because we assume system is stationary. System is stationary. That means the change in kinetic energy and change in potential energy is equal to 0. So what is that? M dot H2 minus H1 is approximately 0. That means H2 is approximately H1. This is the very important conclusion during the throttling. That means enthalpy before throttling, that means enthalpy before throttling and enthalpy, this is your after, not before. Enthalpy after throttling enthalpy before is same. Okay. That means what is the enthalpy before throttling is the same. That means enthalpy doesn't change. But it is not like that, sir, enthalpy will not change throughout process 1 to 2. No, it is not like that. Enthalpy may be changed during 1 to 2, but at 1 and at 2, why? Because this is at a cross section. at A1 and at A2 enthalpy are fixed. That means, see this one. That means if you take this section, please tell me, take this section. If you take this section, beta, my dear, I'm telling you, this is a very good question. Okay. Okay, done. If I take this cross section, let's suppose I take this cross section and this cross section. So let's suppose this is at point 1, this is at point 1, this is at point 1, and this is at point 2nd. So at this point, what is the enthalpy H1? The same enthalpy H2 is there. But during 1 to 2, you cannot say that sir, enthalpy remains same. You cannot say. You cannot say that during 1 to 2, enthalpy is same. That means, my dear, 99% student get confused that sir, throttling is an isenthalpy process. No, it is wrong. Throttling is not a kind of isenthalpy process. What is mean by isenthalpy? What is mean by iso? Isenthalpy or isothermal. What is mean by that? That means if you talk about the isothermal, what is mean by isothermal? Ki sir, state point 1 T1 and state point 2 is T2 are same, but from 1 to 2 also the temperature is same. During 1 to 2 also the temperature is same. That is called isothermal. Like that, if you tell about the isenthalpy, that means at inlet 1 and at inlet 2, though there is enthalpy is same, but you cannot say very conclusively कि sir, enthalpy will same from 1 to 2. So isenthalpy is a so my dear, throttling may not be isenthalpy process. Please. That is the very subtle concept I am telling you. Yes, enthalpy at the inlet is the same as the enthalpy at the exit, but it is not mean that enthalpy throughout the same from inlet to exit. It is not like that. Okay. So here one term is that, hence, yes, it is right. Enthalpy before throttling is the same as the enthalpy after throttling, but that doesn't mean that enthalpy remains constant throughout for the process 1 to 2. Clear? So it is not like that isenthalpy. So throttling is not like that. Now let's see this. There is an example of this throttling. So now let's check this observation. Please tell me. Please check this observation, my dear. What is that? Throttling of an ideal gas. Throttling of an ideal gas. This says that approximately isothermal. Let's check. This is your ideal gas passing through a throttling valve. So what is the temperature at inlet, and there is a enthalpy at H1 you can measure from the throttling device. Now the enthalpy H1 is equal to enthalpy 2. You know, that means this is your at inlet cross section 1 and this is your exit cross section at 2. So H1 is equal to H2. That is right. There is no any problem. That means, my dear, yes, this is right. Sir, yes, H1 is equal to H2. So what is for ideal gas? Ideal gas, what is mean by that? CpT1 is equal to CpT2. That means this Cp cancel out. That means T1 is equal to T2. Yes, temperature before throttling is the same as the temperature after throttling. That means it doesn't mean that temperature is same throughout 1 to 2. So this statement is false. This statement is false. This statement is, please tell me. This statement is false, 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 false. This statement is false. Okay. So throttling of an ideal gas is approximately at isothermal process. That is wrong. Clear? So that is okay. Now, hence, we can say that hence throttling of an ideal gas may not be isothermal process. Yes. Temperature before throttling is equal to temperature after throttling. It doesn't mean 1 to 2 temperature is constant. That is wrong. That is wrong. Clear? So we cannot say that throttling of an ideal gas is isenthalpy process. Yes, 1 to 2 are same. So in the refrigeration, if you measure the enthalpy, so you take the scale at inlet and you have to measure at exit from the same enthalpy. You can approximate like that. It is not like that, sir, during throttling the isothermal process. No, it is not. I give you a challenge. If you have to see anywhere in the standard textbook, please show me. It is not like that. Nothing is to write in here. Sir, throttling is an isothermal process. Clear, beta? Clear this thing? This is clear? Now, so we have to solve this problem. See this one. Please try to solve this problem. That is your very good example of a throttling. Expansion of a refrigerant R13A. What does it mean by A? Just to check. R134A in a refrigerator. What is that, beta? There is a refrigerant 134A enters the capillary tube. So capillary tube, it is also a kind of throttling device. Capillary tube, it is also kind of throttling device. Porous plug is also kind of throttling device. So enters in a capillary tube. Now, my dear, what is the capillary tube? What is the capillary tube? You know this. I will just discuss that one. See, capillary tube of a refrigerator and the enter into the capillary tube. Capillary tube is the very thin tubes. You already aware this term in the fluid mechanics basics class. So enters the capillary tube of a refrigerator and entry point is a saturated liquid. That means this is your tube, my dear. This is your tube. Let's suppose this is your tube. Okay, let's suppose this is your tube, and the fluid will enter, to the throttling device. Let's suppose this is your inlet section. Let's suppose this is your inlet section, my dear. This is your inlet section. This is your inlet section. This is your exit section. Okay. Generally, we have to write 1 and 2. My dear, it says that at a point 1 there is a saturated liquid. Saturated liquid. And what is the dryness fraction of saturated liquid? 0. And what pressure? Saturated liquid at 0.8 megapascal. Okay. And throttle to a pressure. See, the pressure will reduce. So pressure will reduce. That means P2 is equal to 0.12 megapascal. That means during the throttling, beta, P2 must be less than P1. This is sure. This is sure, but temperature you cannot say that. Ki sir T2 less than T1 या T2 greater than T1, you cannot say that. Okay, but pressure you can say. Determine the quality of refrigerant at the final state. That means at this point, you have to find the quality. And the temperature drop during the process. What is that? If it will move from 1 to 2, what is the temperature drop? You have to find it. Some property it is given. Why? Because in the gate question, there is no any availability of the stream table, hard copy. So the data we always provided. So inlet pressure is saturated liquid. So at a saturated liquid, T saturated at 8 megapascal you have. Enthalpy saturated liquid, that is your HF you have. Okay. Now at exit, the P2 pressure you have, but what the second property you don't have. Why? Because minimum 2 property you want. So what is that? You take this property H1. So H1 and that means at exit what you have? P2 is there and also H2 is there. Why? Because H2 is equal to H1. So 2 property you know, you can find the another property. That means at this point there is you have to find dryness fraction. So at this point you have to check this one. So at this point beta, this is the pressure, and that pressure corresponding to you find the saturation temperature. So that saturation temperature is like this range minus. So corresponding to this saturation temperature, you have HF, you have HG. That means what is the HF? HF is the enthalpy of dry saturated liquid. What is the HG? Enthalpy of a saturated vapor. So you have this one. Now, so what to do? Please tell. I am just telling you. Now, so how to find? You just apply. You know this thing, ki sir, during the throttling process, the enthalpy remains same. Enthalpy remains same at inlet and exit. At inlet and exit. So, how to say that? Ki sir, jo H2 value, what is the H2 value? Which is, so see, if you draw the diagram, pH chart, if you draw the pH या TH या HS कुछ भी, you draw the diagram TS diagram, no problem. So this is your diagram. So this is at inlet point, inlet to the throttle, and this is your exit point of the throttling. So inlet, it is a dry saturated point. Okay. Now this is a point at inlet, and exit it is, see, this is 1. Let's suppose exit is it at 2. So 1 to 2 is the throttling process, and this is your irreversible process. So you have to draw the, so H1 is equal to H2. This is your throttling process. Now my dear, so at this point this is saturated liquid. Now what is H2? So if you find, so from this table where it is H2 exactly, we have to find it. See, H2 where it is, see, you at this pressure, at this P2 pressure, why? Because this P2 pressure it is given. Corresponding to this P2 pressure, you can find the saturation temperature. Please. So from the table, if you find the saturation temperature, that is your minus 22.32 degrees centigrade. Clear? Now, at this temperature and at this pressure, you have to find the HF and HG. Now, if you find the HF and HG, this H2 is lie in between that. That means H2 is less than HF and H2 is greater than HG. Yes? See? Sorry. H2 is less than HG and greater than HF. See? This H2 value is how much? 95.48. And this is in between 22 to 232. That means 2 point must be in this region. That means this is your HG and this is your HF corresponding to this pressure P2. This is your P1. So H2 is in the wet region. Now how to find the quality? You know this thing, sir. H1 is equal to H2. H1 is equal to H2, and H2 is what? HG, HF, please, HF plus X HG minus HF. At which pressure? corresponding to P2. Yes or not? Corresponding to P2. Clear? Now, so what is X2? So if you find here, put all this value, H2 you have, HF you have, Hg you have, Hf you have. So if you find X2, that is your value 0.34. Now my dear, this is your dryness fraction. So at this point, at a point 2, if you take a container, in the container, suppose like that, so in this container, 32% of the refrigerant is vaporized. So in this container, if there is this much of a refrigerant is there, this much of the refrigerant is there, so 32% refrigerant it is vaporized, remaining one it is liquid. So accordingly you have to find, and also note down the temperature drop is approximately 53. So during the throttling, the temperature will, in this condition, the temperature will drop. So my question is that why the temperature will drop? I will explain in the next class. So time is over now. Okay, my dear, I hope you enjoyed this video. Thank you. Bye-bye.